Ladies and gentlemen, let's continue with the program, with the next session. My name is Neno Kukuric, and I was asked to chair this coming session with 4 keynote speeches. We will have Professor Ken Howard, you saw this morning, and Professor Milan Dinklage, also saw this morning, and Professor Zoran Stevanovic, and also Professor Hans-Jürgen Braut. So if you allow me, I will start with the first presenter before with Professor Ken Howard. And before I ask Ken to take the floor, I will just say a few words about Dr. Howard, who is, as you well know, current president of IH, and in a long career he was working on groundwater projects all over the world. In 1981 he moved to the University of Toronto, rising to the ranks to become a full professor of hydrogeology with tenure in 1997. As a professional hydrogeologist, Dr. Howard is certified by American Institute of Hydrology, chartered by British Geological Society, and registered as a professional geoscientist with the Association of Professional Geoscientists of Ontario, Canada. He has been a member of the Geological Society of America since 1985, the National Groundwater Association since 1985, and the American Geophysical Union since 1989. He's author and co-author of over 158 articles, including 6 books. Ken, please.
Okay, thank you, Nino. Okay, so for the next little while, I'll be telling you something about groundwater and climate change. We now know that the Intergovernmental Panel on Climate Change have concluded that scientific evidence for warming of the climate system is unequivocal. It's happening. The evidence, well, is pretty much everywhere, beginning with rising temperatures. Most importantly, the last 20 years we've seen a steep rise in global temperatures. We've seen declining Arctic sea ice, rate of change of just over 13% every 10 years, every decade. We're seeing a shrinking Antarctic ice sheet. We're losing over 130 billion metric tons of ice every year. We have disappearing glaciers. As an example here, this is the Muir Glacier in Alaska. This is a slide taken back in 1941. 2004, that's the view from pretty much the same vantage point. And of course, big concern, rising sea levels. During the last century, sea level rose by 17 centimeters, or about 1.7 millimeters per year. In the last 10 years, that rate of increase is now at 3.21 millimeters per year. In other words, almost double what it was during the last century. Well, warming impacts the entire planet. We know it affects ecosystems. It can cause extreme weather events. It increases the risk of more advanced, more rapid climate change and some major irreversible impacts. It will affect our food supply. and of course it affects water. Locally it will cause significant reductions in recharge. It will increase in some areas, but locally decreases in recharge. It will affect runoff in the Mediterranean basin, but with a warming of 4 to 5 degrees centigrade, we can actually see quite substantial sea level rise that will threaten major world cities, London, Shanghai, New York, Tokyo, Hong Kong, the list goes on. So why is it getting warmer? Well, the reasons are quite clearly very complex. Most climate scientists now agree the main cause of the current global warming trend is a human effect, human enhancement of what we have known for a long while, the greenhouse effect, warming that results when the atmosphere traps heat that is radiating from Earth back towards space. We know that several gases contribute to the greenhouse effect, one of the most important ones being water vapor itself, but also nitrous oxide, methane, and probably the main culprit here, carbon dioxide, CO2. It appears to be the key one. For the 1900s, atmospheric CO2 hadn't exceeded 300 parts per million for at least 650,000 years. In May 2013, it actually hit 400 parts per million, and we're still working our way upwards since then. Who is responsible? Well, just about everybody. On the left-hand side there, you can see the percentage of the global total of CO2 that's put into the atmosphere. At the top of the list, we have the EU, we have USA, and China. But if we look on the right-hand side, if we actually look at CO2 emissions per capita, in other words, per person in the population, it's actually Canada and Australia which get up towards the top of the list with the United States, and actually the Europeans don't look too bad. The key point, however, just hidden here at the bottom, notice the average level of emissions required in 2050 if we're going to meet a 400 part per million global outcome. So another 50 parts per million, we've got to get down to this red dash line. So it pretty much means everybody on the list has got to act. So it's a real bit of a background to some of the things that I want to talk about today. I'm going to be looking at some of the potential impacts of climate change on global groundwater resources. The biggest threat comes in areas where climate change will cause a reduction in aquifer recharge. And this map here indicates where we expect to see some significant reductions in aquifer recharge. You'll see the Mediterranean region quite dramatically, or potentially quite dramatically affected. Pockets of South America, also southern tip of Africa, and Western Australia, probably one of the more serious areas. But it's not as if climate change hasn't happened before. As geoscientists, we well understand that climate has been changing very frequently, and in fact, the Sahara Desert, here it is in North Africa, 10,000 years ago was actually much more similar to what the conditions that we get I guess even in parts of Europe. In fact, in North Africa, so beneath the Sahara Desert, we have a number of very large sedimentary basins, And what we find is that storage, aquifer storage, plays a very important role on their development and management. I'm going to illustrate this with some model calculations. This is the base model that was used, a conceptual model. Imagine an aquifer, one of these large sedimentary basins in North Africa, perhaps 400 kilometers across, recharge getting in over a zone of maybe 30 kilometers in our recharge area. Aquifer, let's call it 350 meters thick with a hydraulic conductivity of 1 meter per day, so transmissivity 350 meters squared per day, overlain by a confining layer here, low hydraulic conductivity. We put recharge into this model. We don't need to put much in to fill it up. About 10 millimeters per year recharge, and that will maintain flow. We have a fixed head here, presumably at the Mediterranean, or to represent the discharge point. And what I'm going to do here, I'm going to show you the results of what happens when we switch off recharge instantaneously, go from 10 millimeters per year to 0, and see how long it takes for us to get a response. So, this is the initial potentiometric surface represented by this top line. And we run various model simulations at 0 recharge for a 10,000 year period. And we find that specific yield plays a very critical role. If our aquifer has a very high specific yield, or relatively high, 20%, then the decline is actually quite gradual. Over 10,000 years, we've only dropped in the recharge zone a matter of maybe 150 meters. But even when we have a low specific yield, around about 1%, well, you get a worst case result, but we still maintain heads of well over 100 meters after 10,000 years. The next slide, I'm going to show you what the potentiometric surface looks like across that section. When we're dealing with very high specific yield, here it is, 20%, what we find is our initial potentiometric surface. We only drop by a few hundred meters, around about 120, 125 meters or there. We've got a very significant hydraulic gradient, even without recharge. We've still got flow in our system, and when we drop it down to as low as 1%, we may be down here somewhere, but we've still got flow occurring. In fact, most of the gradients that we see in a lot of these sedimentary basins in North Africa, we call them fossil gradients. They're still there, even though recharge is no longer occurring. But it demonstrates some of the resilience you can get in an underground system if you have high storage. We've also looked at some other African sites. This is some work that we did in Uganda back in the, the late 80s, early 90s, modeling what is very typical, certainly in Central Africa, would be a granite aquifer which is overlain by a regolith, a weathered zone that is typically 30 meters thick, but can be as low as 10 meters thick. So we modeled a number of scenarios for a regolith that has a hydraulic conductivity of 10 meters per day. We looked at a bedrock hydraulic conductivity of 1 times 10 to the minus 2 meters per day, so not a very good aquifer. Specific yield of the aquifer, 0.1%, storativity 10 to the minus 5. But we looked at 4 scenarios: a 30 meter thick regolith with a high specific yield, 23%, a 30 meter regolith with a low specific yield, around about 1%, and the same conditions except with a 10 meter thick regolith. We set steady state initially at recharge of 50 millimeters per year. And then what we did was we instantaneously dropped the recharge from 50 millimeters per year by 50%. We dropped it, 50% reduction in recharge, went from 50 to 25 millimeters per year. And what did we find? We found actually, when we're dealing with a fairly thick regolith and a high specific yield, we didn't reach steady state, and even then, sorry, that's the top one here. The maximum drop was only about a half a meter or so, or maybe just got down to about a meter, and fairly gradual decline. Maybe took 25 to 50 years to actually get down there, just to that little drop. And even with a fairly thin regolith and a specific yield of 1%, even then, the drop is quite rapid with the relatively low storage, but nevertheless, the maximum drop in our potentiometric surface was only, well, sort of approached 3 meters or 3 meters or thereabouts. So again, demonstrating resilience that we wouldn't see in surface water systems. Turning now to saltwater intrusion, storage also plays a role in coastal areas where seawater intrusion occurs. This is a typical scenario we may get: seawater wedge extending inland from the sea. Rising sea levels, we expect those to occur as a result of climate change, but we don't know what's going to happen on the water table. And what happens to the water table is quite crucial in controlling the extent to which this seawater wedge occurs. It's quite a complex modeling system. Similarly, when we pump a well which is in a coastal area, we expect to see upconing of the saline water towards the well. Many of us are familiar with the Geibel-Herzberg principle, where we can calculate what that steady state level would be for an upcone beneath a well. But it is a steady state condition, and in many cases it may take 50 years, 100 years, or even 1,000 years to get to steady state. And I'm going to illustrate this with an island, because we know islands are especially at risk when it comes to saltwater intrusion and rising sea levels. I'm going to look at an island here. It's Elongate Island, 5 kilometers across. And I'm going to be looking at a section essentially across the island from the top to the bottom there. This is what that section looks like. What we find with an island, I'm assuming the hydraulic conductivity is 10 meters per day. And what we expect to see is a freshwater lens develop as a function of the recharge condition. The more recharge we get, the bigger that lens will be. The lower the recharge, the smaller that lens will be. When it comes to steady state, we could actually put all this into a model, but there's no point in using models when there are very simple analytical solutions out there. So to look at the steady state relationship, we use the Henry 1964 solution shown here to calculate where the freshwater lens or the transition from freshwater to saline water is likely to occur. When you have a recharge rate, remember it's 5 kilometers across, a recharge rate of 150 millimeters per year, then the freshwater interface at the center of the island, fresh to seawater interface, is around about 100 meters. When we reduce recharge to 100 millimeters per year, as could occur in a climate change scenario, the freshwater lens is only 80 meters thick, thereabouts. And then if we reduce recharge down to 50 millimeters per year, we're closer to 60 meters. So the lens we expect will shrink. But how long will it take for that to occur? Well, if we instantaneously reduce recharge, we find when we're dealing with systems that have a relatively high storage, this is a 15% effective porosity or 15% specific yield, we find that response is fairly gradual. The top line here is if instantaneously dropping from 150 down to 50 millimeters per year. You can see it takes to reach steady state Well, we're still 400 years down the timeline to actually reach that condition. To just changing from 150 to 100, then again, the drop is very gradual, again, not reaching steady state for several hundreds of years. And that's for an instantaneous change in recharge. When we have lower specific yields, the decline, again, as we might expect, but demonstrate here, become more rapid. The top diagram is for a specific yield of 5%, and the lower one for 2%. At 5%, it still takes 100 years or more, or thereabouts, to reach steady state. It's only when we start to get down to specific yields of 2%, we see a much more rapid decline, a decline or shrinkage of our freshwater lens, still taking maybe 40 to 50 years to occur. So storage plays us a big favor, and we don't often quite appreciate that. Now, fresh groundwater lenses on islands with very steep coastlines will be affected by declining recharge, but not by sea level rise. And the key there is, if the recharge area is unchanged, the key is the recharge area is unchanged. Basically what will happen is sea level will rise in a very steep island, but the water table will also, if the recharge stays the same, the water table will also rise by an equal amount, and the saltwater intrusion will not be affected. So sea level rise is not such a concern with very steep islands. Recharge is the key. If the recharge doesn't change, the saltwater intrusion won't change. This is the concern, however, when you're dealing with fairly flat coastlines, flat islands. When sea level rises, what it does is it reduces the recharge area because it inundates, all right? The coast is here. As it moves across the land, our opportunity for fresh recharge to get in, we get a reduction in recharge, and as a result, we get a shrinkage of the lens. So it's flat islands that we really need to worry about. Personally, I guess having worked with groundwater for so many years, done a lot of modeling, particularly applying or looking at the role of aquifer storage, I'm feeling pretty good about most groundwater systems. They tend to be more resilient or fairly resilient to climate change. And I think the real threats we need to worry about are maybe less so with climate change and how they may affect groundwater resources, but more about the side effects that may occur. And my two greatest concerns are, first of all, the increased demand that will occur for groundwater as a result of surface water supplies becoming unreliable. In other words, if you turn to groundwater, more people will use it. It will increase demand, and I see that as a threat to groundwater levels. And I also am a little concerned about what is touted as one of the potential cures to climate change, and that is CCS, carbon dioxide capture and sequestration by deep burial. The idea is we inject CO2 into very considerable depths, many kilometers, and into non-potable systems. Ideally below an impermeable seal. Nevertheless, I still believe there remains considerable concern that shallow freshwater aquifers will be impacted. So we may be putting the CO2 in down here, but shallow aquifers are still under threat. These are the reasons. First of all, there are physical threats, disruption of aquifer flow systems and groundwater discharge patterns, both natural and artificial, by pressure perturbations. Secondly, there's a concern that saline formation water may be forced into the aquifer, causing the level of the less dense freshwater to rise. And thirdly, fractures may be generated or opened, enhancing vertical permeability. We've heard this before, of course, just like fracking. There are biological concerns too. The CO2 may be used by microorganisms with unpredictable results. Basically, that means the scientists haven't a clue what might happen down there. The CO2 may also mobilize organic compounds from the geological formation, and that may further enhance microbial activity. Probably the most serious threats of CCS, however, are chemical. CO2 may dissolve into the formation water and react with rock, resulting in dissolution or clogging of the storage reservoir. CO2 may seep slowly from the storage reservoir, causing acidification of fresh water in the aquifer and possibly mobilize contaminating metals. CO2 may escape catastrophically around the injection wellhead, causing severe disruption to the freshwater aquifer and, of course, also releasing massive amounts of CO2 into the atmosphere. And also the concern, well, any time we're dealing with great depth, high salinity brines could be displaced from those deeper storage formations and may severely contaminate potable aquifers. Something we often forget is that fractures, faults, and old abandoned injection wells, oil wells, and exploration wells could enhance migration. In other words, they essentially provide avenues for this deep CO2 and the salinities that's related to it to move rapidly up to the surface. We estimate there are something like 400,000 abandoned exploration wells and oil wells in Alberta, Canada, and also probably another 1 million in Texas. And most of them are unmapped, so it's very difficult to locate them and seal them up. It's no surprise that global environmental protection agencies are therefore moving very cautiously with CCS. In fact, the US EPA has been studying this for a number of years, and only the very first, I guess, projects are being, pilot projects are being tested. I have it on pretty good grounds, however, that some of my contacts within the US EPA and some of the universities believe that the CCS may actually never come to fruition at all, so perhaps our greatest hope for groundwater is that CCS technologies will not come to fruition at all, simply because of the costs. The costs make them unviable, perhaps except for rare cases where the CO2 could also be used to enhance the recovery of valuable oil reserves. So it's a technology we may never actually never get used. So, to summarize what I've been talking about today and draw a conclusion, I think unlike surface water, groundwater tends to be fairly resilient to global warming and climate change. However, it will be impacted in areas where aquifer recharge is reduced. When we get a reduction in recharge, it will lower water tables and also enhance seawater intrusion in coastal areas. And it's the low elevations, the flat islands, that are most seriously threatened because we are reducing recharge aerially. High storage systems, those with high values of specific yield, high storage, will prove most resilient and will often offset potential problems for many decades maybe in some cases, centuries. Probably the greatest threat to groundwater comes from a potential cure to climate change, CCS. Specific problems may include major changes to the hydrogeological flow regime and rapid and systematic changes in groundwater pH and salinity. Widespread pollution of major global aquifer resources does represent a key concern. Fortunately, CCS will likely prove economically unviable, which I say is good for groundwater, but it may not be quite so good for the future of climate change. So, thank you very much.